Hello. Uh, Today is a continuation for yesterday's lecture. We're gonna have a look at these equations. Whenever something is moving with a constant acceleration, we can calculate displacement, velocity, time, depending on what other variables are given in the problem. Okay, and these four equations, as I mentioned yesterday, you just memorize them. You are not supposed to know how to calculate them or how to derive them. You just memorize them. Delta x again is displacement, v initial is initial speed, delta t is the time, a is the acceleration, vf is v final. Okay, and then which equation I would use, it depends on what given you have. So today we're gonna practice more with these equations. So we're gonna solve some more problems. And also I want to work a little bit more on motion diagrams. Okay, actually before motion diagrams, let's do one simple exercise where we use these four equations. So they are up here. We will see which equation we will be using. So what is there? Page 5, exercise 5, a speedboat increases its speed uniformly from 20 meters per second to 30 meters per second. So what are these values, 20 meters per second and 30 meters per second? This is V initial and V final, okay? In a distance of 200 meters. So this is over a distance of 200 meters. So I have delta x as well. Find the magnitude of its acceleration. So they're asking me for the acceleration. So I have VI, I have VF, I have delta x, and I need to calculate A. I come and look at all these equations. Which one has VF, VI, A, and delta x? It's equation number 2. I have VF, VI, acceleration, and delta x. So VF square equal VI square plus 2A delta x. If I take VI square to the other side, it becomes VF square minus VI square equal 2A delta x. So 2A times delta x, which is given 200, equal VF square 30 square minus VI square 20 square. I plug numbers, I do calculations. 400A equal 900 minus 400 implies A equal 1.25. Part B, find the time it takes the boat to travel the 200 meters. So I want to calculate delta T in this case. I want to calculate delta T. So I go back to my equations. Which equation has V initial, V final, Vx, acceleration? Which equation? Many of them. Okay, the first one I can use, but there is a squaring, so it's a bit more annoying because then you have to use your calculator in quadratic form. Let's see if another equation can get me delta T. Let's look at the third one. I have VF, I have VF, I have VI, right? I have A, I've just calculated it, and I want delta T. So this is my unknown delta T. This is what I want. I don't have it. I want to calculate it. Okay, so I can use this equation. VF equal VI plus A delta T. VF is 30. VI is 20. Acceleration 1.25. And then I do the calculation for delta T. How do I do the calculation? Same way, I take 20 to the other side and I flip everything around. So 30 minus 20 equal 1.25 delta T. Delta T equal 10 over 1.25. I divide by, I do the division. I get delta T equal 8 seconds. Okay. So let's move on. Sometimes. Okay. Page 11. Exercise number 3. Okay, this is not page 11, exercise number 3. This is actually page 5, exercise number 2. So let me correct it. So this is page 5, exercise number 2. Okay. Forget about what I put here. So let's do it. So what is this? What is this graph? So this is whenever I see a graph where I have V or X or acceleration on the y-axis and I see T on the x-axis, it means I have a motion diagram. Okay, so this is called a motion diagram. On the y-axis, I can have V, A, or X. Okay, and on the time axis, I will have only T. Then this is a motion diagram. And I need to learn how I can get things from a motion diagram. So let's see. Let's read the problem. So the adjacent figure shows a velocity versus time graph for a particle moving along the x-axis. At t equal 0, assume that x equal 0. Part A, what are the particles' position, velocity, and acceleration at t equal 1 second? So at t equal 1 second, I come here, it's in the middle. At t equal 1 second, okay, let me actually first remove all drawings and then put t equal 1 second over here. I need to calculate its position, velocity, and acceleration. From the graph, what is the piece of information I get from the graph? What is the piece of information I get from the graph? It is that at 1 second, how much is the velocity? It's 4. Okay, so at 1 second, the velocity is 4. So I already solved the velocity. What else I need to calculate? Position and acceleration. In this region, from 0 to 2, is the velocity changing? Is the velocity changing? It's not changing. It's not changing. So this is case number 2 that we discussed yesterday. Case number 2, when velocity is not changing, how much is the acceleration? Acceleration is 0. Okay, so these two now, I've got them quickly. V is from the graph, it's 4 meters per second. And acceleration is 0 because V is not changing. And I'm working in this area from here to here, where velocity is not changing. Okay, velocity is not changing. Now I need to calculate the position. I go to these. I can use one of these 4 formulas, actually. I can use one of these 4 formulas, or I can use simply V average is delta X by delta T. Both of them will get me the same answer because here V is constant, implies V average is delta X by delta T. Or I used one of these, which is, for example, delta X is half A delta T squared plus V initial delta T, the first equation. The A is 0, so the first term disappears. Then V initial, or any V here, because it's the same, it's 4 times delta T, it's 1 because it's from 0 to 1. And I get that delta X is 4 meters. So it starts from rest. Did they say it starts from rest? Sorry. No, it started from at T equals 0, X equals 0. So delta X is X1 minus X0, where X0 is 0 because they said that it started at X equals 0. So the position is 4 meters, which is the same as the displacement in this case. Okay, so this is what is happening in this blue region. That's part A. Part B, we need to do the same position, velocity, and acceleration, but at t equal 3 seconds. So now I'm in this region. Now I'm in this region. Sorry, I don't want arrow. Now I'm in this region. And I need to calculate at t equal 3 to 3. So 3 is in the middle as well. Okay. I need to do the calculation for v, a, and acceleration. So what's happening at t equal to 3? How much is the velocity? How much is the velocity over here? It's easy from the graph. It's 2. It's 2. Sorry, let's put it properly. It's 2. Again, it's not so proper. So velocity at t equal 3, it's so easy. At v equal 2 meter, v equal 2 meter per second. I just get it from the graph. Okay. Now, what is the acceleration? This is case number 3 that we discussed yesterday. Case number 3, when the velocity is changing in a straight line with a slope, the acceleration is the slope of the straight line. The acceleration is the slope of the straight line. So acceleration equal to the slope, which is delta v over delta t. And here you can take any 2 points you want. Any 2 points you want. It's not necessary to take the points I chose. It's not necessary. The points I chose were this point and this point. But you can also choose this point and this point, or this point and this point. All of them will give you the same answer. So I took this point and this point. So V final, which is V at 3, which is 2, minus V initial. So this is V initial, the way I took it. This is V initial. And this is V final. Okay, so what is the V initial? It's 4. What is V final? It's 2. So I put it here. V final minus V initial, 2 minus 4, divided by what is T initial? T initial is 2, because here V initial has time equal 2. And this is V final has time equal 3. So divided by 3 minus 2 implies acceleration is minus 2 meters per second squared. Okay. When is acceleration negative? When an object is when the object is moving in the positive direction, but it's decelerating, it's slowing down. Okay. In this case, the velocity is positive, so it's moving in the positive direction, but the acceleration is negative. It means it's slowing down. Now, I need to calculate the total displacement from 0 to 3, which is, they actually want the position, which is the displacement from 0 to 3. To calculate, let me remove everything. To calculate the displacement from 0 to 3, so we are also interested by this point here. This is here our point. Let's make it a little bit more straight. Okay. So what information I have about this point? What information I have about this point? I have its velocity. I have its acceleration, right? These are the type of information I have. Now, what is the position at time equal 3? First, I need to calculate what is the position at time equal 2. So, in order to calculate x3, I need to find delta x from 0 to 2, then add it to delta x from 2 to 3. Okay? So, this object, the particle, it first moved for 2 seconds in a certain way, which is this way, then it moved in a different way. So in order to get the total acceleration, I need to add the position from the first segment plus the displacement from the second segment, which is from 2 to 3. Now, what is happening from 0 to 2? From 0 to 2, the acceleration is 0. So I do like I did in part A. And I get that the displacement from 0 to 2 is 8 meters. Okay. Now from 2 to 3, this is uniform accelerated motion where acceleration is equal minus 2 meters per second squared. So I apply the first formula. I apply it, half A delta T squared plus V initial delta T. A is minus 2. Delta T is from 2 to 3. So delta T is 1. I don't know why this is so better. So from 2 to 3, delta T is 1, right? So instead of delta T, I would put 1. And V initial is this value over here. This is V initial. How much is V initial? It's 4. So my V initial is 4. I plug all these numbers. I get that delta X from 2 to 3 is 3. And delta X from 0 to 2, I already calculated it. It's 8. So delta X from 0 to 3 is 11. I just sum them up. Okay, so I add 8 plus 3 equal 11. Find the displacement of the particle during the first 4 seconds. So I need to do the same thing, but they are only asking me to calculate the displacement this time. So I need delta X from 0 to 4. I will say delta X from 0 to 4, it is delta X from 0 to 2 plus delta X from 2 to 4. Delta X from 0 to 2, it's 8 meters. I calculated it in the previous part. Now I have delta X from 0 to 4. I will use half A delta T squared plus V initial delta T. The only difference now, is that delta T, so here there is 2, and here there is 4. The only difference now is that is that delta T is 4 minus 2, so it's 2. So delta X from 2 to 4 is 4. I added to delta X from 0 to 4, from 0 to 2. I get total displacement is 12 meters. Okay, so notice how from a graph, I could calculate position, displacement, velocity, acceleration, but the most important things I have to keep in mind is that if velocity is a horizontal line, then acceleration is 0. The most important thing I have to remember are these 3 important cases we discussed yesterday. First one, when the position doesn't change, it means velocity 0, acceleration 0. When velocity changes in a horizontal line, implies displacement changes also in a straight line with a slope equal to the velocity. Acceleration will be 0 in this case. And the last case, when the acceleration is constant, velocity changes in a straight line with a slope equal to the acceleration. And the position will change in a parabola, as was discussed yesterday. Okay, let's solve more questions. Okay, page 6, example number 8. A jetliner traveling northward is landing with a speed of 69 meters per second. So what is this 69 meters per second? It is V initial. Once the jet touches down, it has 750 meters of runway in which to reduce its speed to 6.1 meters per second. So what is 750 meters? It's delta X. And what is 6.1 meters per second? This is V final. Okay. Anyway, everything is written on the graph as well. So you can write it here, you can keep it here as you wish. The first part, find the average acceleration of the plane during landing. So we want to calculate the acceleration. What do we have here? We have V initial, we have V final, we have delta X, and I need to calculate acceleration. Okay, so this is in part A. Which equation here has VI, VF, A, and delta X? Which equation? It's equation number 2. It has everything I want. So I will use it. Instead of VF square, I'll put 6.1 square. VI is 69. Acceleration is my unknown. Acceleration is my unknown. And delta X is 750. Okay. Now I start solving the problem. 2A times 750, I can keep it on this side and take 69 squared to the other side and then flip. So I have 1500A is equal to 37.21 minus 4761. I do the calculation, I get my acceleration. Okay. Part B, what is given in part B? What do I want to do? So text again, part B. Part B, find the time taken. So we want to calculate the time. So again, I have VI, I have VF, I have delta X. Now I have A even, and I want to calculate delta T. So how to calculate it? Let me tell you that you can use any equation that has delta T and you can solve it. Because here you have delta X, you have V initial, you have acceleration, and you can calculate delta T or use the last one or use the third one. I used the third one. For V final is 6.1, V initial is 69, acceleration, I have it, so I get delta T. Okay, by some math calculation. Let's move to the last problem for today's lecture. It's number 9. So a drag racer starting from rest means V initial equal 0. Okay, V initial equal 0. Speeding up for 402 meters. So I have this distance from here to here is 402 meters. With an acceleration plus 17 meters per second square. So the acceleration from this to here is 17 meters per second square. A parachute then opens, slowing the car down with an acceleration of minus 6.1 meters per second square. So for the second part, in the second part, the acceleration it changed, okay? How, part A, I changed actually a little bit question. So there is also here X equal 350 meters, it's on the drawing. I changed a little bit the question. So in part A, I asked find VA. And in part B, I asked find VB, okay? And I gave you the answers. So you can do this on your own. And you have to use these 4 equations, nothing else. And just do it on your own and make sure that you get these answers. If you have any questions, if you couldn't solve it or you would like to ask me about something regarding this problem or regarding anything during today's lecture, just send me an email. Okay, so this is the end of this lecture. Bye-bye.